Thanks, Bastian, for the opportunity. So I'm Wilson. I'm a hydroclimate scientist based at the UK Centre for Ecology and Hydrology, and my research mostly focuses on climate variability and climate change and its impacts on hydrological extremes, so floods and droughts. So in this talk, I will talk about the use of storyline approaches for hydrological applications. Much of this work was done during my PhD at the University of Reading, but have continued under my current work, mainly funded through the Canary Project and the Co-Center for Climate Biodiversity and Water. So before I start introducing the storyline approach and its applications in hydrology, I want to start by briefly talking about the evolution of how approaches in understanding the hydrological impacts of climate change have evolved over time. So this paper published at the beginning of my PhD tried to track this evolution through time. So throughout this talk, mostly I will give examples from the UK, but similar methodologies to understand hydrological impacts of climate change is also used and applied elsewhere. So I think there is quite a lot of merit in looking back at how past approaches have evolved and trying identifying their strengths and weaknesses before I then introduce the storyline approach as a complementary kind of way of thinking. So early climate model projections were kind of relatively coarse in resolution, so studies trying to understand the hydrological impacts of climate change did not directly use climate model outputs and instead use kind of discrete, stylized scenarios of rainfall and temperature changes over time. But over time, improvements in climate modeling have led to ensemble projections and kind of a more direct use of climate model output in hydrological models. So this example here shows distributed modeling of hydrological change, river flow changes with an ensemble of climate models. And further computational developments have led to further kind of regional and convective permitting downscaling. So with even higher resolution, model simulations are now available. And this has led to kind of greater ability in understanding kind of multimodal uncertainty. That this is further shown by kind of the emergence of probabilistic projections. So statistical emulators and hydrological models can now be run tens of thousands of times to generate a probability distribution of change. So this example here is from the UKCP probabilistic projections of changes in river flows. There are some drawbacks to these so-called top-down approaches, and in particular, there have been quite a lot of debate on how to interpret probabilistic projections, kind of the assumptions behind the probability distributions themselves, and how they can be treated or used in decision making. So in recent years, approach studies have advocated for kind of a more bottom-up approach, which aims to look at a much wider range of change than the conventional climate projections. So rather than driven directly by climate model projections, we can instead focus on stress testing instead. So this example here shows a scenario neutral approach where a wide range of precipitation changes and the impact of river flows are shown um, looking at a much wider range of change than conventional traditional climate model projections. So these bottom-up approaches tend to have a greater focus on high impact outcomes beyond traditional multimodal ensembles. So this past evolution of methods have led to an exacerbation of or a lengthening of this so-called cascade of uncertainty. So researchers have termed this an explosion of uncertainty. And this cascade of uncertainty shows that projected changes gets larger and larger when cascading from future emission scenarios, for example, down to projected rainfall changes and to local climate impacts, for example, at a river catchment in the UK. And this cascade of uncertainty stems from a number of different sources of uncertainties. It could be the internal variability, could be uncertainty in atmospheric circulation and how they respond to climate change, could be different forcing scenarios, and ultimately it includes uncertainties in downscaling of climate model projections and impact modeling, like hydrological modeling. For example, if we look at a single example of local hydrological change at one single UK river catchment, this is using a hydrological model driven by UK climate projections, we see some agreement over changes in the summer and autumn, but generally for this particular catchment, there is no agreement over changes in winter and spring. For all these seasons, though, the uncertainty range is quite large. And when looking to regional and local scales, these large uncertainty ranges means that the cascade of uncertainty is large. And how do we deal with them? Should we look at the ensemble mean? Um, the conventional ensemble mean approach might end up being misleading, though, and could lead to maladaptation as we're missing out potentially extreme but plausible realizations of climate. So we need better ways to navigate this cascade of uncertainty. And this paper on the right here very nicely showed different ways we can do that. So this concept of a cascade of uncertainty is of course very common across many different climate impacts. And many of those top-down traditional methods that I talked about before often fail to navigate this cascade of uncertainty very well. Well, we can try and analyze as many sources of uncertainties as possible, but we also quickly realize that even the most comprehensive assessment would not be able to fully capture all those sources of uncertainties. So we need new ways to more intelligently crystallize or sample this uncertainty space and provide more decision relevant information. And focusing on just one major source of uncertainty here to start with. So changes in dynamics or how atmospheric circulation responds to climate change has remained a particularly major source of epistemic uncertainty. And climate models project very different changes in atmospheric circulation. And because of this, changes in regional rainfall remains quite uncertain across different models over many regions in both direction and magnitude. So from the point of view of a risk assessment, and particularly at the regional scale, this study here is very nice in arguing that there should be much more focus on the potential for large future changes, especially if the disagreement is large between models. And this map here from this study quantified globally the regions where there are non-robust precipitation projections, so regions where the models do not agree on the sign of change. And for these regions, particularly taking a conventional ensemble mean approach would result in a washed out signal that is quite misleading and ignores potentially large changes that have substantial implication for climate risk. So this is where the storyline approach could potentially complement those approaches I talked about before. So the storyline approach aims to navigate and characterize the cascade of uncertainty a bit more transparently. So in a simplest sense, storylines can be thought of as physically plausible descriptions or a series of what-if hypotheses of climate impacts. And a key to the storyline approach is a degree of conditionality. So storylines seek to explore these multiple plausible hypotheses of climate risk conditioned on specific changes. So these can be either changes in specific drivers of an event, changes in different trajectories of large-scale atmospheric circulation, or changes in kind of exposure and vulnerability. So storylines can be expressed using the causal diagrams, such as the one shown on this slide here, where different suites or different flavors of storylines can be created by conditioning on different nodes of this network. So I will show some examples of applying the storyline approach in the next few slides. I'm starting with a focus on atmospheric circulation storylines, then moving towards how it can be applied in hydrology. So just a note that most of the application and most of the examples I will show are focused on the UK, stemming from my kind of work during the PhD and my subsequent research at UK-CEH. But I will also show some examples from nice work elsewhere in the wider European and international context as well. So I'm sure a lot of people in the room would have seen this already. So the first type of storylines you could create is by conditioning multimodal projections by large-scale atmospheric circulation drivers. So to give a concrete example, this study here is one of the first to apply this concept to multimodal projections, where four different plausible storylines were created to describe changes in Mediterranean rainfall conditioned on different plausible trajectories of how different climate drivers might evolve with warming. So the example here shows that the trajectory or the strength of the different changes in the dynamical drivers in response to climate change can lead to very different changes in rainfall, which are all plausible and equally likely. So don't think there's an objective way of prescribing probabilities to any of these storylines, but exploring them kind of transparently within a storyline approach enhances risk awareness and a more transparent understanding of these uncertainties. So another more local example to me here, focus on the UK. So with this study focuses on jet stream influence on UK weather under a 4-degree global warming. So this study here created four jet stream storylines using multimodal ensembles and showed that given different magnitude of how the summertime jet latitude will change, there is a very wide range of how summertime rainfall across the UK could change. So, for example, an extremely northerly shift in the North Atlantic jet latitude could lead to widespread summer drying, while a less extreme shift in the jet latitude could result in much less drying and even possibly some wetting in northern Scotland. So we can use these storylines to quantify the impact, the implications for hydrology, implications for floods and droughts, given this much wider possibility space. And I will give some examples of how to connect these down to hydrology in a moment. But also, before I talk about that, I also would like to kind of briefly talk about how I think the storyline approach is very suitable for focusing on high impact, low likelihood conditions. So this recent project from the University of Reading delivered a series of hill storylines describing a range of possible plausible atmospheric and ocean circulation changes and its impacts to the UK. So two examples here on this slide shows what if Arctic amplification is stronger than expected, or what if ocean circulation changes leads to stronger than expected temperature or rainfall changes over the UK. A main advantage of a storyline approach like this is we shift the focus away from probabilities. Um, Given the cascade of uncertainties, we can't really estimate robustly probabilities anyways, but instead we try to focus on plausible conditions that could lead to high impacts in order to guard against high impacts that we might want to avoid. So this allows us to look at climate forcings or regional changes outside the range of climate model projections, recognizing some potential drawbacks from climate model projections. Some mechanisms might not be included, but when doing risk assessments, we need to adequately consider a wide range and a full range of possible outcomes. And one other key part of the storyline approach that has emerged is an ability to more adequately consider the influence of internal variability. And particularly at the regional scale, internal variability often dominates for near-term and sometimes even far future climate risk. And this range of internal variability can remain large. And this example here is a very nice recent study, which highlighted a very large contribution of internal variability to Northern Europe runoff throughout the 21st century. So an example of how the storyline approach can help us crystallize this range of possible change is shown by the example here, where the authors advocated for the expression of near-term climate risk using internal variability storylines. Showing, for example, in this example, four storylines were created by conditioning near-term climate change on plausible near-term changes in the NAO and the AMOC, showing that a very wide range of temperature changes is possible, so either slight warming or quite dramatic. Warming in the near future is possible given these uncertain trajectories of the two atmospheric drivers. And internal variability, of course, should be appropriately assessed over the historical period as well. So for kind of a adequate assessment of climate risk, it's important to think of whether a different evolution of climate over the historical period could have led to unprecedented extremes that did not happen perhaps just by chance. So the example here shows by this paper using one particular large ensemble showing that a range of possible trends in historical precipitation over Europe is possible. And if we zoom into a more regional to local scales and not just look at precipitation, but look at more impact relevant variables like river flows, for example, we see the same message holds true. And the figure on the right here is simulated river flows across a wide range of UK catchments driven by a large ensemble, showing that over the historical period, a very large range of annual river flow trends could have been possible. So by chance, we could have seen climate and hydrological trends that are very different to what we have observed historically. And this kind of large effect of climate variability on hydrological extremes means that when we look at floods and droughts, their range of variability is very much undersampled using historical observations. We know hydrological records are often much more variable than rainfall and temperature, and hydrological observations are also much shorter. Most river flow records only begin in the 1970s, So the potential for extreme floods and droughts is undersampled when we look at historical observations. And even before we look at what's possible in the future climate, we don't really fully understand the potential of unprecedented events in the present day climate. So one way of characterizing this internal variability is through the use of initial condition large ensembles. So these are kind of climate model projections with slightly different initial conditions, which leads to entirely different unfolding of weather and climate. And we can think of these as alternative universes where more extreme floods or droughts than the ones in our actual observations could have occurred by chance. And we can apply a storyline approach to explore much of this possibility space. So here's an example for the UK, focused on summer rainfall changes, particularly over the historical period. So the left panel here shows observed summer rainfall on the top and observed summer river flow trends on the bottom over the 1981 to 2010 period. Actually, we've observed quite substantial wetting in the summer over this period. This is despite quite a few generations of climate models suggesting to us that summers are going to be drier. But we also know that climate variability is large, especially when going down to river flows at a local river catchment. So the question we asked in this study was whether the summer wetting we've observed could have occurred by chance, and are there other alternative realizations of what could have happened over the historical period? So here I've used an initial condition large ensemble to drive national hydrological models in the UK to simulate river flows. Now this is shown by the river flow trends again in the bottom row. And if we apply the jet stream storylines I showed before to condition these simulations, which show a southerly jet latitude shift over the historical period, we get quite a strong wetting in the summer for both rainfall and river flows, as shown by the second column here. So the second column here is similar the, to the first column, which in the historical observations. But if we look across the whole ensemble and explore much more of this possibility space through looking at other storylines of jet stream changes, we can see it's quite possible, just from climate variability, that if there was a northerly trend in the jet stream latitude, that could have resulted in substantial summer drying for both rainfall and river flows. So given this particular storyline on the far right, um, we could have seen unprecedented summer droughts that were not seen in the historical observations, perhaps just by chance. And those droughts could have exceeded the benchmark droughts that we use to stress test our water resources systems in the UK. So here I think storylines provide a useful concept to explore more of this possibility space, and it helps raise risk awareness. We're able to much more fully explore the effects of climate variability on hydrological extremes. So I've given some examples of how storylines focusing on past and future trends can be created by conditioning on trajectories of different atmospheric circulation drivers. But another strand of the storyline approach is to focus on individual events. This is known as event storylines, and it's where most of my recent work has focused on. So projected changes in hydrology at the regional scale continue to span quite a large uncertainty range. We can quantify them more transparently through kind of the circulation storylines I talked about. But I think event storylines are really powerful when seeking to provide more decision relevant information. So, for example, we can target a specific historical event and think of plausible stories of how the event could have turned out worse. So, this is known as a downward counterfactual. We can still use climate model projections as a source of information, but in a slightly more imaginative way. So an example I'm describing in this paper here is to focus on the 2013-14 UK flooding. We can ask what if questions conditioned on different nodes of the event's drivers. So for example, we can ask what would this specific event be like if the jet stream state was different? Another suite of plausible storylines we could create would be what if the floods occurred in conjunction with even wetter antecedent conditions? So event storylines, I think, is quite powerful because we're not just looking at simulated events from a climate model, but our analysis is based on actual historically observed events. So it's actually quite easy to connect to people because they have experienced it. One example of a way where event storylines could be useful is for multi-year droughts. So there are like many other compound events, multi-year droughts are rare, and they're significantly undersampled in short historical observations and existing multimodal projections. And climate models may also underestimate persistence of atmospheric circulation patterns, so may not fully represent multi-year rainfall deficits that well. But with an event storyline approach, we can reframe the question from what will be the likelihood of future multi-year droughts, which is quite difficult to answer. Sorry. So what will be the likelihood and impacts of future multi-year droughts is quite difficult to answer. But we can reframe the question to look at what are the conditions that could make up a worst case multi-year drought. So this figure here is from a study, quite a relatively simple example where we picked a historical event. So here we're looking at the 2010-2012 drought in the UK, and we asked a series of what if questions. What if the event unfolded differently? This example here shows what if the drought continued for a third dry winter instead of the rapid drought termination that we observed in the historical event. So winter rainfall in the east of England is crucial because of groundwater recharge, and groundwater recharge depends on winter rainfall. So a very logical and plausible question from a risk perspective is to ask, what would happen if the drought turned out worse? And by rerunning hydrological simulations of river flows with this third dry winter storyline, we show that severe and potentially record-breaking drought conditions could have persisted long after the observed drought termination. So this suggests that this particular 2010 to 2012 drought was a near miss event. It could have turned out worse, and we've been able to enable water companies to stress test their systems against a plausible worst case version of this drought. So whilst uncertainties in how future multi-year droughts will evolve, that uncertainty still remain in climate projections, but we can use the wealth of information we have about historical events and hydrological processes and hydrological process understanding of the conditions making up a worst case drought to create storylines in order to improve our adaptation to future events. So I mentioned the effects of climate variability on hydrological extremes. I mentioned that I think it's hydrological extremes are undersampled. And the simple storyline example from the previous slide, that's based on perturbations to drivers of an event. But approaches like the unseen approach can also be used to sample for these possibilities within large initialized climate model projections. So the unseen approach applied to various hazards have told us that we could have experienced much more extreme events purely by chance. So the figure on the left here is from the Met Office, the seminal figure using the unseen approach, where they used Met Office decadal simulations to look at the potential for record-breaking winter rainfall. And it shows that there is quite a high likelihood of unprecedented winter rainfall in the historical period, which could have been up to 20-30% wetter. So we applied this similar principles to hydrological droughts. So in the middle panel here, it shows quite a similar story. The droughts highlighted in red are events that are more severe than the worst observed drought for this particular river catchment. And it shows that more severe events could have occurred in the past. And understanding this full range of events using these initialized large ensembles, understanding the full range of event that could arise is useful for risk awareness and drought preparedness. And this nature of variability can be better characterized using these large ensembles, and we can create circulation storylines like I talked about before. But we can also try and combine these large ensemble simulations with other lines of evidence to create event storylines. So for example, we can use initialized hindcast archives as a source of information and combine that with our historical observations to create event storylines. So kind of hindcast archives are forecasts issued in the past with the potential of including plausible events that we've not seen before in our historical observations. We can then use those unprecedented outcomes to create worst case storylines. And this example focuses on one particular region in the east of England, where we created 4 storylines of the 2022 drought. And we asked, what if it was followed by different storylines with plausible winter conditions with different atmospheric circulation configurations, such as different modes of climate variability, like the NAO, like the EA. And by running hydrological model simulations using these four storylines, we see that the particular combination of circulation patterns in storyline one could have further intensified the 2022 drought, and we could have broken river flow records established back in the benchmark drought of 1976. So by combining these large sample of plausible unseen events with a historical event, we have a much richer and process understanding of what makes up a worst case drought. Another example of combining model information with historical events to create worst case storylines is for this benchmark drought of 1976. So this was, I'm sure a lot of hydrologists in the room, European and in Europe would know this event very well. So this was a particularly severe event across Western Europe and widely regarded as one of the worst historical drought. And winter 75-76 was characterized by dominant high pressure. The map on the map here shows dominating high pressure over the British Isles over the winter period. And as an example of the hydrological response, I've shown here four river catchments in the east of England, and looking at the drought index, standardized stream flow index here, showing a decline into severe drought conditions over this period. So this drought was obviously quite extreme, but just understanding how a past drought event have evolved is not enough from a risk management perspective. So what is potentially more important is understanding how an event could have been different and asking what if conditions of how this event could have been worse. So for example, we can ask, what if this was with similar atmospheric circulation patterns to the observed winter? And when we run hydrological model simulations with these alternative storylines, we see it is quite possible for a winter with similar atmospheric circulation patterns to lead to even drier conditions and significantly higher drought severity. So these examples show that we can perturb an observed event to look at unrealized droughts or potential near misses. And our storylines here are traceable because it's based on an observed event, and we can easily explore plausible worst cases by taking advantage of large sample sizes from hindcast archives. So turning to the other side of the coin, studies have also applied a similar way of thinking to understand river flooding. So one strand of the event storyline approach I've not mentioned is to inform extreme event attribution. And for this purpose, event storylines are often created by keeping the dynamics of the event as similar as possible to the historical observed event, then looking at counterfactual and factual versions of the event in different climates. And this recent example published recently applies this approach to the widespread floods over the winter half year of 2023-2024. So this was one of the wettest winter half year on record. We saw widespread flooding across the UK and Western France. And we used a circulation analogs approach here to search for events with similar dynamical drivers to the winter half year 23-24. And we searched for these storylines in the recent past versus a more distant past. Then we can make use of hydrological model simulations to look at the hydrological situation arising from those analogs. So comparing the analogs in the recent past with those in the more distant past showed that similar events have become wetter with higher river flows given past climate change. So by keeping the dynamical conditions similar, an event storyline approach like this adds value to extreme event attribution. It extends those results to more impact-relevant variables like river flows using historical observations and historical reconstructions of hydrological conditions from data rescue and hydrological modeling. And keeping our focus on this particular flooding episode, we can further create worst-case storylines by asking whether the event could have been even worse. So this is work led by colleagues at UK-CEH, and a similar approach also applied in the paper recently published, where the wet antecedent conditions of autumn 2023 was quite a wet autumn. So we combined those wet antecedent conditions with different realizations of plausible winter weather obtained from decadal or seasonal hindcasts to create a worst case storyline. So combining the wet autumn with the wettest winter possible in the model ensemble. We see that, for example, for the northwest region in the UK, this could mean river flow peaks being more than 40% higher than what we actually observed. So creating worst cases through a storyline way of thinking is useful to anticipate extremes. It's more salient because they're based on historically observed events, and it combines multiple sources of information from historical observations to model simulations and our understanding of hydrological processes. So to finish off with similar techniques to create these unseen event storylines based on historical events is also applied internationally elsewhere. And this avenue of research has really accelerated recently, and a more kind of storyline way of thinking have contributed to a more routine exploration of worst cases and downward counterfactuals. So we're starting to build up a library of downward counterfactuals for many hazards now. So one approach I've not talked about, but is increasingly used is ensemble boosting, where a climate model is rerun many times to simulate more extreme versions of an observed event. So this particular example here shows, on the left, shows potential for the 2021 Pacific Northwest heat wave to reach even higher extreme heat given climate variability. And ensemble boosting have also been applied quite recently to hydrology relevant hazards like high rainfall and drought. The middle example here shows ensemble boosted storylines of alternative realizations of how the 2021 Central European floods could have unfolded. And on the right is a boosted storyline of a plausible 3-year multi-year drought sequence across Europe by iteratively running climate model simulations and sampling for the driest ensemble member every time step. So approaches like this is useful to create these unseen storylines for hydrology relevant hazards. And a storyline way of thinking encourages us to be a bit more creative, and these studies are a great example of how we can reimagine observed floods by asking what if Hurricane Sandy in the UK, in the US, where the authors created storylines by manipulating the storm tracks, so rainfall is maximized over a certain location. And on the bottom here, floods in the Netherlands in 2021, the authors reimagined how this flood could have turned out if rainfall accumulations centered over different river catchments instead. So we're able to think more creatively about past events instead of treating them as static. And new AI techniques here have also been particularly active in this area. This is a post by colleagues at JBA Consulting, where they worked with an AI weather forecasting model to generate thousands of plausible weather sequences to ask a series of what if storyline type questions. So this is very similar in principle to the unseen approach that I talked about. And finally, this is also increasingly used are in the space of extreme event attribution. So like the example I gave about the winter floods, we can focus on a singular event and we can translate that event in warmer climates whilst keeping the dynamics of that event as similar as possible to the observed. So this could be through the use of analogs, like I showed in the example of the winter UK floods. But recently, promising results were also shown with a reanalysis based system, like the example shown for the storm Ulysses in the UK, which was translated into a warmer climate. It could also take the form of a forecast-based attribution system, which can provide rapid attribution by rerunning forecasts of a target event at several lead times and with perturbations to the sea surface temperatures, for example, as shown by this example here, looking at the winter heat wave 2019. So just a few reflections as a summary as I end. So how atmospheric circulation responds to climate change remains the main source of uncertainty. So projected changes in floods and droughts, particularly the magnitude of change, still remains uncertain. And that's mainly dominated by also by internal variability, which for hydrological events is not well sampled by historical observations and traditional multimodal ensembles. And new classes of large ensembles can help us better characterize this range of variability and sample for unprecedented outcomes. But we can also use those large ensembles to target our search for extreme events, such as exploring more of the possibility space. and also using those large ensembles and combining them with other lines of evidence, such as combining them with historical observations and process understanding, to create targeted event storylines. And I showed a few examples of individual floods and drought events where we're able to base our analysis on historical events that people have been through and people can relate to, and think about what if conditions that could have made that event worse. And this helps raise risk awareness and help us better anticipate unprecedented events in the future, and help decision makers stress test their systems against these worst case storylines. So hopefully I've given you some examples of how storyline approach can be used in hydrology and look at hydrological extremes. And I'll stop there and thank you for listening. Happy to take any questions.